All right, so we talked about this day one of the semester. We talked that. Calculus was pre-calculus. In other words, your algebra and trig, plus the concept of limit. And yesterday we wrapped up our formal discussion of limits with the formal definition of a limit. Once again, that's kind of a preview into the sorts of things the math majors deal with. Jacob, welcome in. And so today we're going to begin sort of the first sort of half, if you will, of calculus, called the differential calculus. This is the study of rates of change. Right. This is why calculus gets used a lot and studied a lot, because a lot of your fundamental principles in chemistry and physics and all that are phrased in terms of rates. And calculus allows us to take and codify and manipulate instantaneous rates of change. So that's kind of where this whole thing is headed. But we're going to start off with a problem. What if I asked you to approximate the square root of 3.8? What's that roughly equal to? Yeah, it's roughly equal to 2, right? Right? And because, well, 3.8 is pretty close to what? So it's pretty much, it's roughly 4, and is it going to be a little bigger or a little smaller than 4? Yeah, minus a bit. So it's roughly 2 minus a bit. Make sense or not? Okay. Now, part of what we're going to do today is figure out a guesstimate for what that little piece is. All right. So that's kind of how I like to start this problem. So if I think about geometrically, get some graphs in here. Whoops. If I graph y equals f of x equals the square root of x, here we go. I've got the point 4, 2 right up there. And if I look at the number 3.8, it's like right around there, right? It's close to 4. And the y value on the graph here would be the square root of 3.8, which is exactly the thing I was asking to guesstimate. You with me or not? Okay. Now, the fact that this function is continuous, continuous means that everywhere on the graph, the limit value matches the function value. But another way to think about continuity is that continuous means that if your close inputs produce close outputs. So continuous means this. Close inputs yield close outputs. So it's really the property of continuity that's having us do this estimation in the first place. You follow? But there's another property of this curve called differentiability that's going to help us approximate that little bit that we're off. Okay? So let's go ahead and fire up Desmos here. And let's look at the point 4, 2, because that's the point that we know about. And let's zoom in here. Now, looking at this graph, is this graph a line? No. But look what happens when I zoom in. It looks like a what? A line. You follow or not? So this property is called local linearity. All right? Now, this is what calculus is good for, especially limits, right? Limits kind of get closer and closer and closer. You follow? They zoom in near the point. And if I zoom in near this point, it looks like a line. And let's suppose I wanted the equation of this line. Well, I think everyone knows one equation of a line, right? What's the classic? Y equals mx plus b. And in this scenario, the m is the what? Slope. And what's the b? Yeah, so the point 0b is the y-intercept. Okay? So this is a handy formula. If you're given the line, you get your slope, your y-intercept, you can build your line. But there's also another equation that comes from the slope formula. So let's remind ourselves, what's the slope formula? How do you get the slope? It's like, yeah, so rise over run. If you wanted to be fancier, you could say that would be the, yeah, change in y over change in x, or y minus y naught over x minus x naught. Have we seen all these things? Okay. So if you take this formulation of the line and you solve for y, you get y equals m x minus x naught plus y naught. And this will be the equation of the line that we're going to have occasion to use here, because m, that's the slope. And instead of being specific and knowing about one point on the graph, namely the y-intercept, x naught, y naught can be any point on the line. Remember seeing this type of stuff before, back in your algebra days? Sometimes it's called the point slope form of a line, right? Something like that, whatever. So what's nice, once again, what's nice, if we're building a line, this can be a little tedious because we could get the slope from any 2 points, but then we'd have to work to get the y-intercept. Here, we can get the slope from any 2 points and then use one of the points to get the line, and then you're done. You follow? So it's a little more streamlined workflow here. So, going back to our picture here, what I'd like to do is, if I could figure out the equation of that line, you follow? Then instead of plugging 3.8 into the curve, which I don't know, I could plug 3.8 into that line, and it would actually be a lot easier to calculate. Does that make sense? All right. So let's figure out what this line is. The point I have, I've got the point 4, 2. So in my scenario, the x naught, y naught here is 4, 2. And what's the slope? Well, we can kind of approximate the slope looking at the picture, can't we? All right. So I go, let's see. So looks like I'm going over and then up. So how far over am I going here? It looks like I'm going over how much? 4 units over, and how much up? So going over there, going up there. So 1, 2, 3, 4 over, 1 up. That would make it a slope of what? Quarter. Okay. So, and once again, this is an approximate because we're using. So this is an approximate. I should do this. It's we'll use calculus later on to actually prove it's a quarter. But there we go. Okay. So I plug this into my formula. I get 1/4 x minus 4 plus 2. All right. Now, could we simplify that? Sure. Am I going to simplify it? No. I'm just going to leave it like this, okay, for reasons that we'll see in a little bit. So what I'm going to do then, I'm going to hop over here and I'm going to dial up this line, y equals 1/4 x minus 4 plus 2. And by golly, can you tell the difference between the curve and the line? Okay. Now, if I zoom out, what's going to happen? eventually you can tell the difference. You with me or not? But this is local linearity, not global linearity. Locally, they look the same. So here's the idea. To approximate the square root of 3.8, this is the following thing. So I've got my f of x is the square root of square root of x. And I'm going to call this thing L of x. L for what? Line. I'm going to call this a quarter x minus 4 plus 2. Okay? And local linearity says that near x equals 4, near x equals 4, the function can be approximated by the lines. Everyone cool with that? In other words, the square root of x is roughly equal to a quarter x minus 4 plus 2. So that means the square root of 3.8 is roughly a quarter 3.8 minus 4 plus 2. Now let's actually work this out. This would be 1/4. What's 3.8 minus 4? Negative 0.2 plus 2. So here's that 2 minus this. Now what's a quarter of 0.2? I'll put the 2 first. What's that? Well, what's half of 0.2? Will be half of 0.1. You follow? So by golly, look at that. It's 2 minus a what? A bit. And so this works out to be 1.95. You follow? So we wanted to know what was the square root of 3.8? We knew from continuity, we knew it should be 2 minus a little bit. So what did we do? The square root of 3.8 is roughly equal to, so this is the y value on y equals f of x equals root x. 2 minus 0.05, 1.95. And this is the y value on y equals L of x equals this. Okay? You follow the big picture what's happening here? I'm taking a curve. I'm approximating that curve with a line so I can approximate y values on the curve with y values on the line. Are we all cool with that? So once again, here's the visual. I'm going to call this thing L of x. And I'm going to look at f at 3.8. That's the actual retail value of the square root of 3.8. It's 1.949, blah, blah, blah. Okay? Here's the value of the line at 3.8. There's that 1.95 we calculated. You follow? Is that a good approximation? Yeah, that's pretty darn good. You with me or not? Okay. In fact, we could use this line to approximate all kinds of numbers. All kinds of values close to 4. For example, what's the square root of 4.01? I don't know. It's a little more than 2. The linear approximation is 2.0025. What's the actual retail value of that? Pretty close. You with me or not, folks? This is the idea of local linearity. Okay. Anyone taking physics or will take physics? These classic problems in physics is the pendulum problem. Pendulum problem. And they write down a differential equation that describes the motion of the pendulum, and they tell you, joke's on you, you can't solve this. So what we do is they talk about this small angle approximation. And as long as your theta is measured in radians, you're going to see this. The sine of theta is roughly theta. All right? How are you going to get away with that? Well, let's find out. Let's switch over to the sine. And when they say small angle approximation, they mean theta is roughly 0. You follow? In other words, you're not moving the thing very much. So, here's the sine function. Once again, we're using radians here. Let's zoom in. And by golly, that wavy sine wave, boy, it sure looks like a what? Sure looks like a line, right? If we're looking here at the origin, our x naught and y naught are both what? 0, 0. Now I just got to figure out the slope. What's the slope appear to be? However far I go over is exactly how far I go up, right? So the slope appears to be what? 1. You dial all that in. Sure enough, I get y equals x. You with me or not? So, near 0, there's the function that gives you the sine. There's the function that just gives you the thing back. Can you tell the difference? No. It's locally linear. Now, of course, as you move away, right, it gets really, really bad. But locally, so small angle approximation, sine of theta is roughly theta. Right? So you get real, like for example, the sine of 0.05 is going to be roughly 0.05. Remember, this is radians. So it's got to be in radians for that to work. So local linearity is a very powerful thing. It can be used to help approximate, but it also can help us we can also use it to help us make predictions. Right? You follow? Like if I tell you information about a function, here's y equals f of x. If I tell you f of 2 is 5, all that tells you is information about that point. You follow? If I told you that the limit as x approaches 2 of f of x is 5, then that tells you that around here the function values are getting closer to 5. But it doesn't tell you which direction. You follow? What if I told you that the slope at x equals 2 was 5? Well, not do 5. Say it was 3. So that means if I zoomed in here, it looks like a line, and that line has a slope of positive 3. So what's that look like? What's positive 3 look like? Is that increasing line or decreasing line? It's an increasing line. So locally, it looks like this. You follow? So now that tells you not only what's happening near 5, but also gives you a direction. You with me or not? It tells you what the thing looks like locally as a line. It's increasing there. So you would expect if you put in values more than 2, you're going to get values that are more than 5. You plug in values less than 2, you're going to get things less than 5. Does that make sense or not? So there's more information about this. All right. Well, what if we wanted to actually figure out, what if we wanted to prove these slopes? So let's start off with, let's look at the f of x equals root x at x equals 4. We wanted to prove the slope at x equals 4 is in fact 1/4. Because once again, we glean stuff from a graph. And we know that we may not have zoomed in far enough. You with me or not? It seemed to work. But anytime you look at graphs and tables, that was the one the one question on the test. I gave you a table of values, right? What's going on with that? I was very happy. Most of you wrote, well, it's a table. I mean, there's lots of different variations on the theme, but most of you understood the idea that you could have predictions from left to right based on the table, but at the end of the day, there's still an entire interval of real numbers between those values, and you can still get closer and closer and closer, and pretty much anything could happen. Right? So I wanted the proved slope is 1/4. So let's introduce some notation. So here's some words. Sometimes this is called, let's start off here. The notion of tangent line. Okay? So tangent line is what we're going to be calling this, the line. That's the name of the line. That's going to be like our L of x. That's our best linear approximation. When you zoom in, if you zoom in and you see a line, we're going to call that the tangent line. Tangent comes from your old friend tangent. Tangent typically means it just touches, right? That's what tangent means. We're going to call this the tangent line. Let's go back to the square root one. So we can kind of see the tangent-y kind of thing happening here. The line comes in, moves away. Okay. So that's why it's called the tangent line. But for us, the tangent line means this is the line that we zoom in and get. All right. So if you have a function that's locally linear and you zoom in, that's the line we get. So the slope of the tangent line is sometimes denoted as m tan. Okay. Sometimes it's denoted as f prime. So this is called the derivative of f at a. And what this represents is that this is the slope of the tangent line. So if you see that little apostrophe there, that's pronounced prime. It's called the derivative. It's a derived function. So if you say something is derived from something else, you've started with something, you've done something to get something else, right? Something is a derivative of something else. So we start with our function, and then this slope, you can get this slope from the function itself. So f prime at 4 means I want the slope of the tangent line at x equals 4. So how are we going to do that? Because normally for slope, if I think about the slope formula, it's your change in y over your change in x. Right? So normally you have 2 points, x naught, x1, x naught, y naught. x1, y1. You have 2 points on the line. You take your change in your y over your change in your x. You follow? So here's the challenge with this tangent line. The only point I have on this graph that I know for sure is on the tangent line is the point 4,2 itself. You follow? I don't have another point. You with me or not? This is where we're going to have to do some calculus. So what about this idea? What if instead of starting with the tangent line, what if I start with something else? What if I pick another point on that curve? So here's what we're going to do. Here's the point we care about, 4 comma 2. You follow? Here's the line we care about. Our tangent line just comes in and does this. So I'm going to pick another point. I'll call it A. So I'll pick it over here. Here's some value A. And I'll connect these dots. Right? This is called a secant line. A secant meaning to cut through. So I only have one point on the tangent line. I can't make a slope with that. So I'll pick another point on the curve that's close to that point. I'm going to call that the secant line. And let's look at the slope of the secant line. That's your change in y over change in x. And what would that be? So let's see. We would have your a comma f of a here, which would be your a comma square root of a. So we would have the square root of a minus 2 over a minus 4. And that would be my slope of that secant line. Here we go. And I'm going to put a comma f of a on there. All right, so I'm going to take this off and take that off. Okay. So here are, so you see how this red line is the secant line. You see how it cuts through at 2 points? You follow? Now what happens as I move? What happens as I move my a value closer and closer to 4? You see what's happening in that secant line? It's becoming more and more like the what? Tangent line. Okay, and then the same from over here. Okay, so if I put the tangent line up there, you can see what's happening. You with me or not? Okay, so this is where the limit idea comes in to help us with these slopes. All right, for slope we need 2 points. On the tangent line we only have 1 point. Solution, we'll make a secant line. We're using 2 points, and we'll move that second point closer and closer to the original point. The secant line will then turn into the tangent line. Make sense or not? Okay, so that's the big principle here. Is that if I want the slope of the tangent line, I can take the limit of the slope of the secant line as a goes to 4. All right. I think I want to call it. Yeah. Let's just call these x's. So then x can move. And then we'll have the limit as x goes to 4. Okay. So let's check it out. Slope of the secant line. That's your change in y over change in x. So once again, here's 4. I'm just going to call this x. We're on this curve. We've got 4 comma root 4, which is 4 comma 2. And we've got x comma root x. So we would have the square root of x minus 2 over x minus 4. And so the slope of the tangent line would be the limit as x goes to 4 of the slope of the secant line, which would be the limit as x goes to 4 of square root x over, minus 2 over x minus 4. And let's take a quick moment to make sure everyone understands what's going on this slide. because this is the heart and soul of what we're going to be doing. This is the main concept that drives the theory for the rest of the 2 chapters. So we all dialed in on what we're trying to do. We're trying to find that tangent line. We have a point on the line, no problem. We need the slope. Now we got to figure out the slope. For the slope, we need 2 points. We don't have 2 points. So we'll take 2 points on the curve. And then we'll push the 1 point closer and closer to the point we care about. And then the secant line will turn into the tangent line. So we all hip on what's going on there? Are we good on that? Okay? All right. So, first thing we try and limit is what? For anytime you encounter a limit, the first thing you try is direct substitution. So we'd actually plug in x equals 4. Now, plugging in x equals 4 would be the same as plugging in the same point to the slope formula. You're always going to get a what on top and a what on the bottom. So every single one of these problems will be a 0 over 0. You follow? Good thing we spent a bunch of time last week figuring them out. You follow? How do we handle one that's got radicals? Conjugate. So, first note here is every slope of the tangent line will be a 0 over 0 indeterminate form. That's part 1. And so that means we're going to have to use what we learned in chapter 2. So in this particular case, we're going to hit it with the conjugate. What's the conjugate do for us? In the numerator now, I get root x times root x, which is? What happens to the middle terms? Minus 2 times positive 2. Do we ever multiply out denominators? Once again, the reason is we're hoping that we can get that x minus 4 to cancel. So we wouldn't multiply it out. We didn't have to cancel again. Sure enough, what happens? In the numerator, what goes? What's left in the numerator? 1. Anything stopping me from plugging 4 in here? Boom. Was that the slope? That slope we got experimentally. You follow or not? So the slope of the tangent line, aka f prime at 4, is 1/4, and so my L of x is exactly what we thought it would be. Okay. In other words, we had zoomed in far enough to see the slope that the calculus gives us analytically. So this is the whole process. Everything you're going to be doing here for the next couple of days is finding slopes. And you'll be finding slopes using limits. That's all that's going on here. Slopes, slopes, slopes. So we got some big definitions here. You got a function f. The derivative of f at x equals a, denoted f prime of a, is f prime of a equals the limit as x runs off to a of f of x minus f of a over x minus a, provided the limit exists. Right? You have experience of where you get a 0 over 0, but it still doesn't work out. You follow? There's one like that on either the test or the take-home. Geometrically, what this represents, f prime of a is the slope of the tangent line at a comma f of a. So you come in here, I'll draw this a little bit. So there's the point a comma f of a. Here's your tangent line. The slope of the tangent line, that's your f prime of a. Okay. You understand where this comes from and what it's trying to do. We're good with all the notation. This is more words. To get the tangent line, we call that L of x. The formula for the tangent line then would be f prime of a times x minus a plus f of a. Right. That's your slope. And the point on the curve is a f of a. So these are the two big formulas we'll be working with. And then there's a variation of the one. But all right. Let's do an example. Let's look at f of x equals 2 over x. Find the equation of the tangent line. Well, let's say at x equals -2. So the equation of the tangent line, y equals f prime of a times x minus a plus f of a. So let's go through each of these pieces. First thing is, what's the a value? What x value are we interested in here? We want the tangent line at -2. So that's our -2. So now what we need to do is we need to find f of -2, which is what? -1. And now we need to figure out f prime at -2. And this is where we got to do our calculus. Okay? This is where we have to do our limit. So f prime at a is the limit as x approaches a of f of x minus f of a over x minus a, which means f prime at -2 would be the limit as x approaches what's the a? -2 of f of x minus f of -2 over x minus -2. Right. You see where we're plugging in and what we're plugging in? So a is the point on the graph we're concerned about. So now we plug in everything. I got the limit as x goes to -2 of f of x, which we know that is what? 2 over x, minus f of -2, which we got was -1. And x minus -2, that's the same as x what? Plus 2. So let's simplify this a little bit. and then talk about how we're going to resolve this limit. Because we know ahead of time this is going to turn into what form? It's going to be a 0 over 0. So f, whoops. So f prime at negative 2 is the limit as x goes to negative 2 of 2 over x minus a minus 1. That's 2 over x plus a 1 over x plus 2. And by golly, if you plug in negative 2, in the numerator you're going to get a 0, and in the denominator you're going to get a 0. So there's a chance this will work out. How do I handle fractions like this? What do I got to multiply by? Yeah, the little denominator. In this case, there's only one little denominator. That's what? X. Multiply by x over x. Take the limit. X runs off to negative 2. Multiply. What's 2 over x times x? 2 plus x. Do I multiply out the denominator? No, because we're hoping we can get the x plus 2 to cancel. That's the whole goal here. By golly, will it cancel? Yeah, because look at that numerator. It says 2 plus x, but that's the same as what? X plus 2. That's your commutativity for you. Can I now cancel out? Can I plug negative 2 in now with any issues? So what's my final answer here, folks? Negative 1/2. So once again, this limit represents the slopes of those secant lines. We're picking 2 points on the curve, 2 over x. We're focused in at negative 2 comma 1, and we're looking at the slopes of these lines as they come in to negative 2, and the limit of that slope is negative 1/2. That should be the slope of our tangent line. So now we go back to our tangent line. F prime at negative 2 times x minus negative 2 plus f of negative 2. And we got that derivative minus 1/2 times x plus 2. And then what was the function itself? Negative 1. And once again, feel free to simplify. We'd have a minus 1/2 x. And then what would happen here? And then we'd have another what? There it is. Now, what's the ultimate check that this really and truly is the tangent line we're looking at? What should happen? If I graph the original function at the original point, and I graph this line, what should happen as I zoom in near that point? They should become indistinguishable. You follow? So let's do it. Over x. We're looking at the point negative 2 comma negative 1. There it is. Boom. And what did we get for our tangent line? Minus 1/2 x minus 2. So here we go. This is the big reveal. Ooh, there it is. Do you see the local linearity? Right? If you start zooming in on there, what's going to happen? Yeah. You with me or not, folks? Okay. You can start plugging in values. Plug in like L of negative 2.1 versus F of negative 2.1. You see how close they are? Okay. That's local linearity. Okay. All right. So let's review the handout here. We'll talk about this formula here in a minute. Okay, so once again, when we finish today, there's going to be plenty of other things for you to do. So we got a video here on example 2, working out more of these. Example 3, working out more of these. Example 4, working out more of these. So here's the definition of the derivative. Let's talk about this other formula here. So we've talked about this one. So where the heck does this come from? Well, it comes from a slight little relabeling. So let's talk about where this formula comes from. Then we'll practice it on the two functions we have, and then we'll talk about rates of change. All right, so what we're doing now, the way we're trying to get at derivatives now, we've got this a comma f of a, and then we've got x over here, x comma f of x, and the slope of the secant line. That's your change in y over change in x. That's your f of x minus f of a over x minus a. And so then our derivative would be the limit as x goes to a of f of x minus f of a over x minus a. So this is what we've been running with here for the last 20 minutes or so. Okay? But there is another way to phrase this exact situation. So here's what they do, is they look at the difference between a and x, and they're going to call that value h. All right? So that means that if I wanted to express x in terms of a, I could do it. X would be a plus what? H. Everyone cool with that? So this point, I could rephrase this point as a plus h comma f of a plus h. You follow? So another way to rewrite this slope is it would be f of a plus h minus f of a over, and then what would happen? I'd have a plus h minus a. What would happen to those a's? They would cancel out. You follow? Now, as x gets closer and closer to a, what does that mean in the land of h's? If x and a get closer together, h is going to get what? Smaller and smaller. It's going to go to what? 0. So we could write this as the limit as h goes to 0 of f of a plus h minus f of a over h. It's an alternative means to get to the same end. You follow? Each formula has its advantages and disadvantages. You want to be good with both. I find this formula is easier to show when a function doesn't have a derivative, which we'll talk more about tomorrow. This one is easier to get formulas for derivatives. And we'll see that tomorrow as well. All right. What I really like about both of these is that if you remember where this comes from, delta y over delta x, that's your delta y over delta x. That's your delta y over delta x. You follow? Just remember that these are limits of slopes. So let's look at f of x equals root x. Let's look at f prime at 4 using this alternative definition. We'll show you how this works. Now, if it comes to like the test, because this will be obviously on the test this week, or the take-home, I will tell you what formula to use. You follow? I will give it to you. I will say, use the limit definition of derivative, blah, to find this. I tell you which one I want you to use. Okay. All right. So, oops, I forgot to put the f prime of a over here. All right. So we're looking for f prime at 4. So 4 is what goes in where the a's do. You follow? So f prime at 4 equals the limit as h goes to 0 of f of 4 plus h minus f of 4 divided by h. Let's first make sure we understand what we're plugging in. We're always plugging in for the a's here. We're good with that? Now we have to go back and do some algebra. f of x is the square root of x. So what's f of 4 plus h? That means everywhere you see an x, either literally or in your mind's eye, you want to put parentheses around that x. And you want to replace it with what? 4 plus h. You follow? So that's the correct expression there. The 4 plus the h, all that goes into the square root. Are we okay with that? It doesn't do this. This is the common mistake. That's different. This would be f of 4 plus h. You follow? These are different things. This is the one you want. So that's why I tell my students, either literally or in your mind's eye, envelop that x in parentheses and erase the x from the parentheses and replace it with the 4 plus h. Right? Okay. So f prime of 4 is the limit as h goes to 0 of f of 4 plus h, that's the square root of 4 plus h, minus f of 4, square root 4, over h. That's the limit as h goes to 0 of the square root of 4 plus h minus 2 over h. And you can check, but it's a guarantee. Anytime you're doing these limits for derivatives, you're taking the limit of a slope, and when you directly substitute, it's essentially trying to plug the same point in for the slope. So you will always get a 0 over 0. So once again, what's our tool to rectify this? Conjugate. All right, what do we get here? Root 4 plus h times root 4 plus h is 4 plus h. What happens to the middle terms? What's negative 2 times 2? Do we multiply out the denominator? No, because we're hoping we can get that h to cancel out, right? That's the whole goal. All right, what happens to these h's? Can I plug in h equals 0 now? What would I get? The over square root of 4 plus 0 plus 2. By golly, that simplifies to what? 1/4. So you get the same answer. It's just a different way to approach it. Any questions on the setup on this one, or then the execution of it? All right, let's go back and do that other one. We had f of x, we had what, 2 over x. And we wanted to find f prime at negative 2. Once again, using the formula, f prime of a equals the limit as h goes to 0. F of a plus h minus f of a over h. We should get the same slope we got before. In this particular case, we want the derivative at negative 2. So for us, f prime at negative 2 would be the limit as h goes to 0 of f of negative 2 plus h minus f of negative 2 all over h. Now I got to do a little algebra here, because here's the f of x is 2 over x. What's f of negative 2 plus h look like? That negative 2 plus h is going to go where? In the denominator. So it's going to be 2 all over negative 2 plus h. You with me or not? That whole thing goes in there. F of 2 is 2 over negative 2 all over h. Okay. Everyone see where all the pieces parts are coming from and how they're getting all plugged in. Keep in mind, all we're doing is finding slopes. That's all we're doing. Slope, slope, slope. I got a 2 over minus 2 plus h minus a negative 1, so that's a plus 1 all over h. And once again, we're presented with a complex fraction. How do we rectify this? We're going to multiply top and bottom by what? That little denominator. Multiply the first term. What's going to survive there? 2 plus 1 times negative 2 plus h. Once again, we're hoping we can get that h to cancel out, so we're not going to multiply it through. And sure enough, how's the numerator simplify? H. This is a running theme in calculus so far. It'll continue into the next chapter. We simplify numerators and factor denominators, because that's where things could go wrong. Sure enough, what happens to those h's? Anything stopping me from substituting in h equals 0 now? Sure enough, what do I get? Same thing I got before. You follow or not, folks? Okay. So you should be comfortable with these formulas and using them. There are, 6 or so examples, more examples of different types of functions where we go in and use both of these formulas. Once again, this thing is called the derivative. If the derivative exists, we say the function is differentiable at that point. Right? So the quality of having a derivative is called differentiable. What differentiable means? Geometrically is locally linear. If you have a derivative, that means that you have a slope of a tangent line. That means you've got a tangent line. That means if you zoom in near that point, you're going to see a line. Here's the equation for the tangent line that we talked about. Okay. So let's talk about rates of change. So your slope, that's a rate of change. You know, when you think about it, you got your line, like if your slope is like a 5/2, that means for every 2 units you go over, you go up 5. That's what slope means. It's a rate of change. But rate of change are out in the wild. For example, I don't know, the price of gas per gallon. That's a rate of change. Right? It's whatever, $3.50 per gallon. You with me or not? That's a rate of change. How does the price change compared on the quantity of gas you buy? So in general, if I look at f of x, I think of x as the input and f of x as the output. And so when you look at any of these slopes, like f of x minus f of a over x minus a, this is a rate of change of outputs to inputs. Now back in pre-calculus, you talked about the average rate of change. So this is called an average rate of change. Okay? So for example, the temperature at 7 in the morning was 59 degrees. Say it's 59 degrees Fahrenheit. And let's say the temp at what? 9 o'clock. Let's say it's 64 degrees. Then you could calculate the average rate of change of the temperature. If you took the change in temperature over the change in time, that would be what? There's your 5 halves, right? There's your 2.5, and that would, what would the units be on that? The numerator is measured in what? Degrees Fahrenheit. The denominator is measured in hours. This would be 2.5 degrees Fahrenheit per hour. That represents the average rate of change of increase in temperature. You follow or not? Does that mean it was going a constant rate all the time? No. It probably was a little slower than the sun comes. You follow? But that's an average rate of change. What calculus gives you, this gives you the instantaneous rate of change. So how fast is the temperature changing at this instant? Okay. Another way to describe this is your average speed versus your instantaneous speed. If you drive 100 miles in 2 hours, what's your average speed? $50 miles per hour. That would be your average speed. Does that mean that you were going 50 miles an hour the whole time for 2 hours? No. I mean, that's a possibility, right? You just set the cruise control and go. But more likely you sped up and then you slowed down. You with me or not? What the speedometer is telling you is it's telling you a derivative. It's giving you an instantaneous rate of change. How fast are you going now? You with me or not? Okay. So that's another way to think about what's happening here is the calculus gives you the instantaneous rate of change by taking a limit of the average rate of change. And so this is a nice little thing to remember. The difference between the function value and the derivative, both geometrically and in terms of inputs and outputs. So let's look at this example. Suppose capital T of lowercase t represents the temperature in degrees Fahrenheit t hours after 6 a.m. on a particular day. Right. So capital T of t, this is the temp, degrees Fahrenheit. T is the number of hours after 6 a.m. Interpret T of 2 equals 20. So the key here is inputs and outputs. The input here is what? 2, which is a little t, which is a what? Yeah, so little t is 2. 2 hours after 6 a.m., that's what? So we're at 8 a.m. Big T is 20. Big T is what? Temperature. So at 8 a.m., it's what? 20 degrees Fahrenheit. You with me or not, folks? Okay? Now, contrast that with T prime of 2 is 4. So T prime of 2 is 4. Once again, the input is the same. The input is what? 2, which is a T, which is hours after 6 a.m. So this is still at 8 a.m. You follow? Same time. But this 4 now is a what? It's a derivative value. That means it's a rate of change. So this 4 has units attached to it. Right? It has units of outputs over inputs. This function is outputting what? temperature, degrees Fahrenheit, and the inputs to it are what? Time in hours. You with me or not? So this 4 really is 4 degrees Fahrenheit per hour. You with me or not? Now, is it a positive or negative number? So does that mean this temperature increasing or decreasing? Increasing. It's a positive slope. You with me or not? So this means that at 8 a.m., the temp is rising at a rate of 4 degrees Fahrenheit per hour. You see the difference between the function and the derivative. The function gives you the output, the derivative gives you the rate of output to input. At 2 p.m., the temperature is 36 degrees Fahrenheit. So we want to write a little math equivalent to that. Okay? So at 2 p.m., well, 2 p.m., that's a t value. What time does that correspond to? It's 8 hours after 6 a.m. You follow? So t would be 8. 8 hours after 6 a.m. The temperature itself is 36. Now, is that T or is that T prime? T. So T at 8 is 36 would be equivalent to that statement. Make sense? At 2 p.m., the temperature is falling at a rate of 3 degrees per hour. So at 2 p.m., the temp is falling at a rate of, 3 degrees per hour. Okay. So at 2 p.m., that's the same time I had before, so little t is 8. But now they're telling us about a what? A rate. That means they're talking about the derivative. So t prime of 8 would be what? Negative 3. The negative because it's falling, and the 3 is the rate of change, 3 degrees per hour. Make sense or not? So this is why calculus is important to all of these disciplines, because it's how people talk about rates. All of the big laws in physics, force equals mass times acceleration, right? Newton's second law, big one. Acceleration is a rate of change. It's actually a rate of change of a rate of change. In chemistry, you do all these labs with chemical kinetics and stuff. It's all those rate laws are phrased in terms of rates. They're all actually derivatives in the skies. So what would it mean if the derivative is 0? Yeah, so if the derivative is 0, then that means that there's no change, right? That means that things are what? What's it called if there's no change? Still or constant is the more mathy way to do it. Does that make sense? Let's think about it here graphically. What's an example of a constant function? So graphs of constant functions are horizontal lines, right? What's the slope of a horizontal line? 0. You follow? So if your derivative is positive, that means that we got an increasing slope. If the derivative is negative, that means we've got a what? Decreasing slope. And if the derivative is 0, then that means, whoops, you with me or not? So there you go. All right, last example is a physics E1. So we alluded to this earlier. So a position function, typically called S of t, It represents where a function is, or where an object is rather, at time t. So S of t tells you where you are. The instantaneous velocity is the derivative of the position. So that tells you how fast and in what direction. The speed is the absolute value of the velocity. That tells you the how fast. The sign plus or minus tells you the direction. So if you're looking at vertical motion, for us, positive means you're getting higher off the ground, so that's going up. Minus means you're getting closer to the ground, going down. Make sense? If you're going left and right, right's positive, left's negative. So here's a formula. Gives the height of a model rocket above the moon's surface as a function of the time after liftoff t in seconds. So we're looking at feet seconds. Find and interpret S prime of 15. So let's work through this one together. And then that'll be it for today. So they want S prime of 15. And we've got a couple of different formulas to use for that. So these are the two derivative formulas we've got. We have f prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. We have f prime of a is the limit as h goes to 0 of f of a plus h minus f of a all over h. So we've got two things to pick from. It doesn't matter which one we use. You follow? So let's just use the first one. So S prime of 15 would be the limit. Now here's the thing. The variable here is not x, it's what? T. So we need to put that in there. And then the a, the number we're looking at, is what? 15. So this would be the limit, not as x goes to a, but rather t goes to 15. And instead of f of x, it's going to be s of t. Instead of f of a, it's going to be s of 15. Instead of x minus a, it'll be t minus 15. So before we get any further, is everyone okay with the new lettering now? We're good with that? All right. So we'll go to the next slide here. Okay, the s of t, that's given to us right there. Minus 5t squared plus 100t. I need s of 15. So I got to plug 15 in for t. And I'm just going to, looks like it's 375. Right? Over t minus 15. And if you plugged in t equals 15, you can bet dollars to donuts you're going to get a 0 over 0. So that means we have to try to simplify this. So what strategy can we try here? For once there's no radicals. For once there's no fractions. There's just a quadratic. So we try to do what? Try to factor. Now, since plugging in 15 to the numerator gave me a 0, I should be able to factor out a t minus 15. That's, once again, your factor theorem. Let's see if this works. What would you have to multiply to get to the 5t squared? Okay. And what would you have to multiply to get to the negative 375? What's 375 over 15? What's that? 25. So what happens to the t minus 15s? Cancel. Now is there anything preventing me from just plugging the 15 in? So I get negative 5 times 15 plus 25. So when the dust settles, I get a negative 50. Okay. So that's the fine part. So S prime at 15 is negative 50. Now for the interpretation, you need to tell me what that means in terms of this rocket. So the derivative of position is your velocity. Right? So it says that the velocity when t equals 15 is negative 50. So 15 is 15 what? Seconds after liftoff. So 15 seconds after liftoff, what's going on with this rocket? Is it heading up or heading down? It's heading down because the velocity is what kind of number? Negative. It's heading down at what rate? 50 feet per second. You follow? So S prime of 15 equals minus 50 is the same as saying V of 15 is minus 50. This means 15 seconds after liftoff, the rocket is traveling downwards at a rate of 50 feet per second. So once again, that downwards we know is coming from that negative there. Make sense or not, folks? Okay. So, big takeaways from today. Differentiable means locally linear. Geometrically, if you have a graph and you can zoom in and get a line, that's what differentiable means. We want to get the equation of that line because we want to be able to approximate or learn about the function from its tangent line, the local linearity there, the tangent line property. What do? We got to find the slope and a point on the graph. The point on the graph we already have. The slope, how do we get the slope? We take 2 points on the curve and we nudge them together. Okay? That visual we did on Desmos, hopefully that's in your head. We take the slope of the tangent line is the limit of the slope of the secant line. So once again, the pre-calculus idea of slope coupled with the notion of limit gives us the calculus notion of slope of the tangent line derivative. All right? You've got some extra examples to do from the handout that'll walk you through using both formulations of that. So make sure you look, go through those. What examples? 2, 3, and 4. And then you've got homework then from the book to work on.